Okay, hello, good afternoon. My name is Johan Blondelle. I work at European Commission, DG Research and Innovation, and I form the link between the Commission and the battery partnership BAT4EU. I'll be moderating this session together with Professor Silvia Bodoardo from Politecnico di Torino. Yes. So we will be talking about solid-state batteries this afternoon. And just to let you know, last week with the partnership, we adopted the new Strategic Research and Innovation Agenda. And solid-state batteries are still very prominently listed in there because anyone who knows the sector hears that there are many announcements, many promises, but still a lot of work to be done because nothing is on the market yet. So this afternoon we'll be hearing from 3 projects that are providing very important stepping stones to putting these products on the market. And aside from the technological aspect of the solid-state batteries, so the promises for higher density, more safety, and so on, the projects have also been asked to look into life cycle assessment and recycling, because these are also very important components in terms of the policy, as we want to move towards circular economy, including for batteries, and also the life cycle assessment, which is a very important component for the digital battery passport, which will enter into force in 26-27, if I'm right. So from a practical perspective, each of the speakers will get 15 minutes sharp. We will have the session, the debate session afterwards, which will be moderated by Silvia. And I think this is all we need to know. Just a reminder, this is a hybrid session, so please wait for the microphone to arrive before you ask your questions. So then, I would like to ask the first speaker, that is Sophie Maillet. She will be presenting the project ASTRABAT. She holds a PhD in electrochemistry, works at SAFELiMOVE, and has been working on batteries for 15 years. The floor is yours.
No. It's not working? Ah, okay. Okay, so thank you very much to be here for ASTRABAT project. So ASTRABAT means all solid-state reliable battery for 2025. In this project, we have developed new, eco-friendly, and all solid-state lithium-ion batteries suitable for electrical vehicles. The overall project presentation is to investigate effectively new material. And in your case, we have decided to consider high voltage NMC cathode and silicon anode. In this case, we are in the Gen 4A generation of all solid-state battery. The idea effectively is to use a silicon anode that allows us to keep flexibility and also to avoid delamination that could occur in general with the lithium metal electrode when there are some lithiation and deletion. Interest of all the all solid-state batteries also to be able to develop specific electrolyte following the side of electrode. For the cathode, in this case, we have used PVDF materials. For the anode, or MOSER, that is an inorganic organic polymer. And we involve also in this project LLZO as a unique ceramic conductor. The key figure of the ASTRABAT project is the following. It's a project that was funded under the LCBAT 2019 call, and in this case we are 14 partners that involve in the project. from research and technological organization, academic sector, and also SME and larger industries. With the consortium, we cover all the value chain from materials up to the end user, with ELAF and Stellantis as example as end user of the technology. Objective of the project is the following. We have 5 main objectives. First of all, effectively, it's necessary to work on the development of materials. In this case, we have defined a specific KPI related to the ionic conductivity, the performances, the cyclability, also inside the project. So you will see this later inside the result. The second objective was also to consider processing technique. The idea is that to go rapidly on the gigafactory is to be able also to use some process that are already known. Then we have a third objective that is related to the new design of cell architecture following power and energy application. So in this case, we have developed some model. Today I won't present this, but you will see in the handbook of the ASTRABAT that there are also some model that has been developed in the case of this new generation of lithium-ion cell. And then, effectively, there's a part related to safety. We use solid electrolyte in this objective. And the last one is related to structuration of the whole value chain of the whole solid-state battery, including eco-design and end-of-life and recycling. So recycling is also something that has been addressed inside the project. Here you can see the first result related to the development of anolyte and catholyte materials that are associated to the ionic conduction. As I said to you, we have developed hybrid electrolyte, integrated catholyte and anolyte in this case. The KPI, 0.2 millisiemens by centimeter, was considered to validate this electrolyte. In the both case of anolyte and catholyte, we obtained the KPI at more or less 50 to 60 degrees. For the atmosphere, we have selected different and tested different types of lithium salt, LiTFSI, LiTDI, and LFSI. And also, we have added some plasticizer in order to increase the conductivity. The plasticizer is ionic liquid. It is used in a content of 15% that allow to keep the solid aspect of the materials. For the catholyte, it is the same thing. We have tested different types of lithium salt. Here it is mainly reported LiTFSI and LFSI. And also we have tested different weight ratio of ionic liquids, and also added some ceramic material in order to be able also to develop a thick layer that is only ionic conductor on the top of electron materials. This is what has been done here with the LLZO powder. So as I said to you, we use ceramic in this case that could avoid the formation of dendrite and block this dendrite at the level of the thick interface between the both electrodes. LLZO powder is also very interesting because they have the conductivity and the KPI at low temperature. In this case, at 20 degrees, we obtain already the KPI that are expected. Here you can see that we have an easy-to-fabricate membrane with the mixture of PVDF and LLZO. And this material has been tested in half cell with NMC 622 versus lithium metal at 25 degrees. And the cycling has been done up to 100 cycles at 0.2 C as cycling rate. So it's stable, and the result was very interesting in this case to continue with this formulation for the full cell. At the side of the silicon anode, it is something slightly different because, first of all, it was difficult to formulate this electrode, and we have a specific curing step that is limiting for the different steps where we would like to address all the cell. However, so the results are the following. We have tested different lithium salt, and in thin electrode, we obtain a good stability up to 100 cycles and a large capacity, so a reduced capacity retention. So the value obtained is more than 1,500 milliampere-hour by gram, in this case, with the LFSI materials and ionic liquids. This is a two formulation that has been retained for the fabrication of full cell. As I said to you, the idea was effectively to use a classical method and process for manufacturing electrode. Here you can see some example of push shell that has been done with 22 milliampere-hours. Some example also of the cycling stability of this material is the following. Following the two electrolyte thickness, we have effectively some impact related to the electrolyte thickness and ionic conductivity that decrease slightly the discharge capacity. And after, when we are at a higher C rate, effectively, it is the kinetic that is limiting the process, and we are able only to keep 10% of the capacity of the cell. Mid-term to long-term expected impact of the project. This project has been reported up to now in four publications, addressing silicon electrode, addressing also the lithium, the ink formulation of electron materials. But as I said to you, for the future, it's also necessary to consider recycling. So we have beginning the work of recycling development of the ASTRABAT solid-state battery with two steps. First of all, a pyrometallurgical step that allows us to obtain the NMC-rich black mass, that is aster, treated by hydrometallurgical route. And the result show that we are able to extract more than 90% of the material in the NMC black mass. So we have obtained in this case nickel sulfate and cobalt sulfate that could be recycled for the different approach. The overall recycling efficiency is lower due to the fact that in this put shell we have also some aluminium and also different polymers that are limiting the recycling. But if we increase the capacity size of the cell, we are also able to decrease this packaging impact. From this project, we have also developed some new technology, new knowledge, and we have also initiated some work on bipolar cell as an example to increase the power of the technology. As I said to you, we have also worked on the development of screen printed electrode or inkjet printing electrode in order to adapt the knowledge that we have got from modeling to the design of the electrode materials. And we have also initiated some large-scale development at UNESCO with 1 ampere hours, and in this case, the stability has been validated at C/20. In conclusion, this project has initiated some work of hybrid electrolyte cell, and we have demonstrated the capacity to test cell up to 1 ampere hours. The main difficulty is the management of silicon electrode and the difficulty also to access to all the capacity of electrode materials. Bipolar cell is also something that is new and is considered inside the project. And cell manufactured by inkjet and screen printing require ink optimization that could be addressed in the future for the design of new lithium-ion cell with all solid-state technology. I would like to thank you all my colleagues involving in this project, and also Yolande Murat that is helped me inside the coordination. And thank you.
Thank you very much. Perfectly within time. Unless there are any burning questions now for clarification, I propose that you keep your remarks for the Q&A session afterwards. And with that, I would like to ask the second speaker. She is Maria Martinez Ibanez from CIC Energy Gune. She has a PhD in applied chemistry and polymeric materials, and at CIC she works on polymer solid-state batteries. And she is going to present the project SAFELiMOVE.
Okay, good afternoon everyone, and thank you for the introduction. As he just presented me, my name is Maria Martinez. I'm coming from CIC Energy Gune. It's a research center in the north of Spain. And today I'm here as coordinator of SAFELiMOVE project. So first of all, I will explain what SAFELiMOVE stands for, and it's Advanced All-Solid-State Safe Lithium Metal Technology towards Vehicle Electrification. So first of all, I will provide a brief overview of the project, starting with the rest of the partners. So here CIC is the coordinator, but this work has been performed thanks to the joint effort of 15 partners, where we are covering the whole value chain. So we have universities and research centers, and we go up to cell manufacturers and end users. So SAFELiMOVE project, as it has been explained for ASTRABAT, was granted in 2020 under the College 2020 LCBAT 1 2019. And the length of this project is 48 months. So this means that SAFELiMOVE project was finished the 31st of December of last year. The budget of this project was close to 8 million. And as I was saying before, this was split between the 15 partners. So going more to the technical details of the project, I want to provide a general overview of the objectives. So when we were conceiving this project, we decided to divide these objectives into 4 main pillars. The first one, of course, is related to the materials, innovative materials development, where we have the 3 key components into the battery, that are the cathode, the electrolyte, and the anode. Later, I will provide more details on the chemistry that we selected, but just for you to understand a little bit, for the cathode, we were seeking for a material that could be able to provide high specific capacity. For this reason, we choose nickel-rich NMC type of materials, NMC 811 in this case. Then for the electrolyte, we decided to combine the advantages of inorganic and organic materials, so mainly seeking to a synergistic effect where we were able to reach high ionic conductivity as well as a high voltage stability to be coupled with the NMC type of materials. And then in the anode side, of course, we were looking for being able to reach really high energy densities. So for that, the material that was selected in our case was lithium metal. And more exactly, we decided to work with lithium metal foil, so avoiding the use of copper that will have an impact on the total energy density that can be achieved with this battery. Then the second main pillar is related to the optimized interfaces. So as you can imagine, we have different types of materials. So this will lead to a system with many different intra and interfaces. So for that reason, a lot of effort has been done not only on the studying the interfaces or the phenomena taking place at these interfaces, but also on the development of interfaces that are able to be stable when we couple different types of materials. Then the third pillar is related to the cell design and processing. So we need to consider that at the end we are talking about a new chemistry, a new technology So there are many challenges that have been faced during these 4 years in order to scale up this technology to prototype scale, several ampere-hour prototype scale. For that reason, a lot of effort has been devoted since the very beginning to design how will be the scaling up not only of the battery, but also of all independent components. And then the last pillar is related to the future market vision. So here we have been working on the cost model development, on recycling and life cycle assessment. So here we need to consider that recycling has been addressed from the theoretical point of view, because we are in an early stage where we don't really know how is the chemistry that we will have at the end for being able to design the recycling, experimental recycling work. And also, of course, we have worked on the development of a roadmap towards 2030. Now going more into the details of the quantitative targets. When we designed the project, we divided 4 different phases. So our KPIs were clear by means of cell impedance, cell energy density, and cyclability. Some of them, of course, were already defined by the call, but we decided to split them into the different phases of development of the project. So in the first phase, we developed our level 1 material. We consider this as the proof of concept where all the different components were put together, and we needed to learn and understand how was the compatibility. And these were used to produce the Gen 0 monolayers or coin cells of the project. From the learning we gained here, we developed the level 2 materials that in this case was scaled up to be produced, to produce the first generation 1 ampere-hour cells of SAFELiMOVE. Again, guided by this knowledge gained through the cycling, aging, post-mortem analysis, we developed the last generation of the materials of the project, level 3 materials. And in this case, we decided to use this material not only for the second generation of 1 ampere-hour cells, but also to go further up to 10 ampere-hour cells, the first and the only generation of 10 ampere-hour cells of the project. And then in the last phase, we wanted to challenge more ourselves, and then we decided to go to the battery module of 24 volts and 10 ampere-hours. So now I will present the results through the time. So starting from the very beginning, level 1 materials, as I was saying before, were selected. So NMC type cathode active material. Then we decided to use a hybrid catholyte. So in this case, our binder was a conductive polymer electrolyte, where we were combining again organic and inorganic phase. Then for the electrolyte, we had another type of polymer and another type of inorganic filler. So mainly we wanted to design ad hoc electrolytes or layers to be in contact with lithium metal and to be in contact with the cathode, because at the end we need to consider that the requirements of the lithium metal are not the same requirements of the cathode. And then the last component, the anode, we use a lithium, self-standing lithium metal with non-copper of 50 micrometers. All these materials were transferred to the partner in charge of manufacturing the cells, Tech in this case, and they produced the first coin cells and the first monolayer pouch cells. So the main outcome of this, so for sure this was in the month 7 of the project, we were not looking for reach all the KPIs, but the most important outcome that we got here is how was the compatibility of all these materials when we were putting them together. We need to consider that each material was provided by a different partner, so it was really important to make this checkup. And then also we analyzed the cross-section and the post-mortem of this cell. So what is the failure mechanism? What is the degradation or the failing issue of my battery? And thanks to this, we understood where were our challenges and how we could solve them. So for me, by means of the cathode, for sure in the level 1 materials, we were talking about a low loading of 1 milliampere-hour centimeter square, so we were really far from meeting the KPIs. So the main challenge, how can I go 3 times higher on loading to 3 milliampere centimeter square? Then improve the conductivity, because we already talk about how is the conductivity of the electrolyte, but there is also a lot to do into the cathode side. So then we work on improving this point also into the cathode, and the stability of the NMC. So we know that the stability of the NMC 811 might be an issue during the handling, also during the battery operation. So for that reason, we developed different coatings for these particles. In the case of the electrolyte, the main challenges were related, among different challenges, the main challenges were related to the mechanical properties. So we developed a cross-linked network in order to improve the integrity and the mechanical properties of the electrolyte. And also we needed to increase the ionic conductivity. So we play with different molecular weights of the type of polymers in order to push this property. And then on the case of the anode, there are two different topics. So from one side, we wanted to further increase the energy density, so we needed to decrease the thickness of the lithium metal, so we went from 50 to 40 microns. And then also we wanted to improve the interface stability, so we work on coatings strategies for the lithium metal. All this together led us to the first generation 1 ampere-hour cells that were, again, manufactured by CDTech. And they were shared with the rest of the partners in order for being tested by different means. So we evaluate how was the performance at different rates, how was the cyclability, how was the cell resistance, how was the safety. And here I'm presenting the cycling performance of this first generation of 1 ampere-hour cells and the obtained KPIs by means of energy density. We were around 240 watt-hour per kg, while in the case of the volumetric energy density, we were close to 400 watt-hour per liter. And the main, or the key point, is that from the level 1 materials to this second generation of materials, we were able not only to scale up, but also we need to consider that we triplicate the loading of the cathode, we decrease the thickness of the lithium metal, and we were able to reach more than 100 cycles with these energy densities. Nevertheless, there was still a lot to do, and this took us to the last part of the development at material level. So this is the case of the level 3 materials, where we developed a double-layer electrolyte, where we wanted to have a LATP-rich layer in contact with the cathode to improve the stability, electrochemical stability, and a soft interlayer in contact with the lithium metal, that this was a polymer-rich layer. So these materials were used to develop the second generation 1 ampere-hour cells. And in this case, we found how here we are comparing the performance in blue for the first generation and in green for the second generation of 1 ampere-hour cells. And we could see how we could reach, in this case, a higher both gravimetric and volumetric energy density of 350 and close to 700 watt-hour per liter. All these cells, even though the project is finished, many things are still ongoing, mainly because of the timing. So we hope that we will be able to compare our results versus the KPIs soon. And then the last part, in parallel, we scale up to 3 ampere-hour cells. Previously, I said 10 ampere-hour cells, but because of how challenging it is to really scale up a new chemistry for the cathode, the electrolyte, and the anode, and also the manufacturing and all of them, finally, for the from the safety point of view of the project, and for being able that we were, and for making sure that we were able to reach these important milestones of SAFELiMOVE, we decided to reduce the capacity of the cell to 3 ampere-hours. So the format was fully different. So in previous case, we were working on 5 by 6 centimeters square, and in this case, we are 18 by 8. We changed the shape, but we decreased the number of the layers. And these cells were provided to another partner, Ikerland in this case, that were able to develop the VMS. So as you can imagine, going from new chemistries up to the VMS in 4 years was really challenging. And of course, in some cases, and in this case, we needed to take some risk mitigation plans, like decreasing the capacity of the cell. And the good point is that the KPIs of the module were fulfilled related to the cell resistance and the state of charge paradigm development. However, by means of the energy density, we were not able to meet it, mainly because you can consider that we are talking about cells with 3 ampere-hours. So this means that the weight of the module and the volume of the volume is impacting a lot on this. So we were not able to reach these KPIs, but at least we were able to prove that the module that was developed was working, as well also by means of safety, the parameters related to the overheating, over voltage or over current parameters. So this was the last milestone of the project. And then I will be brief on this part. So there are also other activities that has been performed. So for example, related to the dissemination of the project, we have released 7 newsletters of the SAFELiMOVE project together with other 3 of the LCBAT 2019 cluster. We have been in more than 20 international conferences. We have 5 publications in scientific journals. Of course, this is not only CIC, it's the whole consortium. We have organized an invited session in TRA Lisbon on 2022, representing the cluster together with other clusters in the field. And also, last October, we organized as a cluster activity a workshop related to innovation and networking days on solid-state battery technologies in Grenoble. It was hosted by ASTRABAT, and this was the last event of our cluster. And then, how much time do I have? 2 minutes, okay. So, monitoring the KPIs. Here, I wanted to compare. I think it's nice to see how the technology has evolved along these 4 years. So we have the Gen 0 monolayer, where we have energy density of 150 watt-hour per kg. So if we compare to the target that we defined, we were around 30%. Then with Gen 1 1 ampere hour cells, we were able to push this value up to 246 watt-hour per kg. As well, we were able to improve the cyclability of the cell compared to the Gen 0 cells. And mainly Gen 2, where all the improvements that we apply to the cell and all the learning that we monitor and we gain during the development allow us to reach an energy density of 350 watt-hour per kg and close to 700 watt-hour per liter, and as well reduce the cell resistance. So the cyclability, as I said before, we have 80 cycles, but cells are cycling by the different partners, so the results are still ongoing on this regard. And if we compare to defined KPIs, we can see that by means of energy density, we reach the 80% of the energy density. In the case of the volumetric energy density, we are below, we are around 55, 60%. By means of the cell impedance, we have fulfilled the target. And then the cyclability, as I was saying before, this is a value that is still ongoing. And then I wanted to highlight the main challenges of the project, because it's not only about saying what is the outcome, also what we have faced during these years and the learning that we are taking out from here. And I will say that the most challenging part, of course, at material level, there are many things that we can do at lab scale for meeting KPIs related to, for example, ionic conductivity, thermal stability, anodic stability. But then we need to consider how this is going to be a scale-up. And these are the main challenges that we have faced related to the manufacturing of the thick solid-state electrode, the manufacturing of the hybrid ceramic polymer electrolyte layer, and the manufacturing of the 10 ampere-hour cells, 3 ampere-hour cells at the end, mainly because of the lithium metal handling without any type of current collector. And then the learnings is that we really need to put a lot of effort when we conceive an idea in this type of projects on thinking about something that is going to be really applicable and scalable. So the closest that we are to the current facilities to take advantage of that already the investment has been done, the easiest that will be to push the TRL of this technology and faster, of course. And also the close communication that we should have. I think this is a good point of this type of project. So academy and industry are working together, and I think that this is really important to agree and to align from the very beginning to make sure that we are able to reach at the end the milestones or define KPIs. And this is just really fast. So the impact by 2030, so this project has been finished, so we do not have a short-term impact because it's done. So by 2030, of course, we consider that by means of energy density, we could impact further if we improve the engineering. I think that at material level, of course, there are things to do, but the engineering of the cell, it's really important, like loading of the cathode, active material content, thickness of the components. So I think that here we can improve a lot to push further the KPIs. By means of safety, we perform already some safety tests. At material level, safety, of course, polymer electrolyte is safer compared to liquid, but that's true that at cell level, we still need to understand how are these mechanisms, and there are tests that are being performed by CA, in our case, in our cluster. And the cost is difficult to predict, of course, considering the assumption of high volume production and the cost model that was developed within SAFELiMOVE. We foreseen to reach 100 euros per kilowatt hour, and this could be further reduced, but also depends on how the market evolves. And I would like just to thank you, everyone, and sorry for taking a few minutes more.
Thank you very much. Now we go to the final presentation of this session. The project SOLiDIFY was going to be presented by Louis de Taille. Unfortunately, he fell ill, but he will be replaced by his colleague Daniele Di Lecce, also from IMEC.
Thank you for the introduction. So, my name is Daniele Di Lecce, and I will present briefly, I will show a brief overview on the SOLiDIFY project. This is an Horizon 2020 project which has started as well on the 1st of January 2020. It was supposed to be a 48-month project. However, due to the challenges we are facing in developing this solid-state technology, we ask an amendment with an extension of 6 months, so the results we'll see today are not the conclusive results of the project. So as you can see from the name of the project and the acronym, this project is based on a liquid to solid solid-state technology. Oh, wait. What have I done?
You need to press. Wait, ahora no sé. You need to press here and then
Ah, okay, thank you. Sorry for that. Okay, so IMEC is coordinating this project. However, we have 14 partners which are located in several countries, several European countries. And thanks to the synergy between these partners, the idea of the project was to cover the entire battery value chain, which goes, for example, from the material development, the optimization of the cell component, for example, the cell integration, the component integration in a cell and in a battery, as well as the upscaling to mass production. Another important point is, as it was mentioned, the life cycle assessment and the recycling of the battery. The SOLiDIFY battery is, as I mentioned, based on a liquid to solid processing of the electrolyte. So in this battery, we have a conventional composite electrode, which is infiltrated by a liquid precursor, the liquid electrolyte precursor, which then is solidified in situ onto the electrode and within the porosity of the electrode. And this enables, is expected to enable an achievement in terms of rate capability due to a maximization of the contact area between the electrode components and the electrolyte solution. And at the same, in a similar way, we also perform a lamination of the lithium metal anode, and then the two components, the two impregnated components, are sandwiched together. The main component of the cell is a polymerized ionic liquid-based electrolyte, which impregnates the cathode and is laminated onto the anode. The cathode is based on a trenched architecture, which I will describe later. And then another key aspect of the cell is the protection of the lithium metal anode in order to avoid the formation or mitigate the formation of lithium dendrites. Another aspect which is also taken into account is the upscaling of the process, and I will mention a few things about that in the next slides. So, as I mentioned, the main component of the cell is this nanosolid composite electrolyte. It is based on a polymerized ionic liquid, which may have different characteristics depending on the electrolyte composition. So as you can see, we can tune the ion conduction properties by changing the electrolyte composition, and for example by adding an inorganic dopant. And we can achieve an ionic conductivity approaching 1 millisiemens per centimeter. The characteristics of upon lithium plating and stripping can be also tuned by changing the electrolyte formulation. This electrode has a quite wide electrochemical stability window, which enables its use with NMC 811. And another important characteristic of the electrode is its flexibility. So it is an elastic electrolyte which may accommodate the variation in volume which we may expect from plating a high capacity of lithium metal. The cathode is prepared according to a trenched architecture which was developed by one of our partners, where we can achieve a capacity up to 12 million per hour per centimeter square. This trench architecture is particularly suited for accommodating the liquid electrolyte precursor. We may increase the thickness of the electrode and the loading without a substantial loss in terms of rate capability. Other two topics where we have been working on are the optimization of an open current collector architecture, as well as the nano coating of the active material particles in order to improve the lifetime, the cycle life in the cell. The lithium metal anode is the last component which we have been optimizing. In principle, the cell is assembled in a discharge state, so we could use a lithium-free electrode. However, we need an excess of lithium in order to mitigate the due to the loss of lithium, irreversible loss of lithium caused by parasitic processes in the cell during the first cycle. One of our partner has a high efficiency process, PVD process for depositing lithium at high rate, and we could achieve, we could get a lithium electrode with an overall thickness, including a carbon collector of 30 microns. This electrode is then protected or optimized by forming an artificial interlayers, and in this regard we have been working together with EMPA on protecting the lithium current collector, and this is reflected as an improvement in terms of cycle life of the cell. Another aspect which we have explored is the optimization of a 3D structure current collector to decrease the local current density in the cell. And this improvement in terms of at component level led to an improvement in terms of cell prototype. So at the moment we are working between the coin cell and the monolayer pouch cell, and we can get an aerial capacity of 8 million per hour per centimeter square, which corresponds to an energy density of slightly above 700 watt-hour per liter. So the challenges we are currently facing are mostly related to the increase of the electrode loading, the cathode loading, and at the same time the decrease of the separator thickness, which may cause the failure of the cell. One goal of the project is the upscaling the pouch cell to the a multi-layer pouch cell, and then the upscaling of the existing process in order to match the characteristics of the existing production line. So we basically want to move to a roll-to-roll process. where we aim at producing lithium anode and a cathode in a continuous roll-to-roll process at a scale which is higher than a kilogram scale. However, this we are as well facing some challenges which are mostly related to the trench architecture, which is difficult to upscale. Another challenge is due to the impregnation of the electrolyte within the architecture of the within this trench architecture. In principle, the electrolyte can be manufactured by doctor blade coating, and we expect some improvements, which perhaps may follow in a follow-up Horizon Europe project. In terms of mid to long-term expected impact of the project, the main impact are mostly related to the higher thermal stability of our chemistry compared to the conventional liquid electrolyte cell. So in general, we may expect a lower amount of inactive cell components in the cell. So a further increase in energy density when we move from material level to pack and vehicle level. So I already mentioned some key innovations we have provided, or we have been providing. One key component is the polymerized ionic liquid composite electrolyte, which is typically investigated within the European Union. The high efficiency production of lithium metal anode with a protected surface is another aspect which we may identify as a key innovation, along with the particle coating, which is developed by one of our partners and enables the continuous coating of powders at high rate. And lastly, the trench architecture is one of the it's another key innovation which is particularly suited for this technology, where we impregnate the electrode with a viscous liquid solution. So the SOLiDIFY project aimed at increasing the TRL from 3 of this technology, which was the TRL we estimated before the start of the project to TRL 6, and we expect the targets are quite challenging. However, we expect a possible further improvement due to the transfer coming from the transfer of the technology to the mass production. And finally, eventually, we expect to strengthen the European leadership in battery technologies within this area. So thank you for your attention.
Thanks very much, perfectly in time. With that, we finish the presentations and we start the Q&A session. So I'll hand the word to my partner in crime, Silvia Bodoardo.
Thank you very much. So thank you very much to all the speakers, in particular to be on time, so that we have time for many questions. I guess that the main issues were all related to scale up. So let's think about going to TRL 6 or what else. And there are differences between the 3 projects. So please, the floor is open to the audience if you have some questions. Is there someone that wants to break the ice? No, they were so clear. Okay, there, please.
Hello, I'm Jordi from IREC. One question for Maria. Why did you choose LATP for like the solid electrolyte? Did you study that before, or?
Okay. Okay, so thank you for the question. So actually, because of the time, I didn't really go into the detail of the chemistry selection, but actually the motivation was to define a bilayer system from the very beginning, where we have a type of chemistry for the electrolyte and a type of chemistry for the catholyte. And this took us also to the selection of different type of inorganic materials. So LATP is not really compatible with the lithium metal. So for that reason, at the very beginning, in the Gen 0, we were using it in the cathode side, while garnet does not present issues with the lithium metal. So it was chosen for the part of the lithium metal anode. However, when we move into the second material generation, we started to face some issues related to the reactivity of garnet surface, because we wanted to have a hybrid material with a semi-interpenetrated network, so a polymer that was cross-linked, so there were some functionalities, but then the garnet was reacting with the polymer, so not in the way that we wanted, but it was decomposing the polymer. So for that reason, we shifted from the garnet to the LATP, even if we knew that we had some risk on the compatibility with the lithium metal. But after the cell testing and the post-mortem analysis, we found that covering the particles of the LATP with the polymer, we could solve the issues with getting in contact with the lithium metal. So mainly the motivation at the very beginning was to have both type of inorganic fillers, but at the end the selection took us to LATP, mainly because of the challenges of garnet during the handling, because it's really sensitive, and also during being in contact with the rest of the components of the cell.
Other questions? Please, Anwar.
Thank you very much for...
Can you just also introduce yourself so that also for the audience?
Yes, Anwar
thank you very
Alias
much.
from Rice. My question is on the SOLiDIFY project. So my first question is like, how about the scalability of this polymerized ionic liquid electrolyte? Is it is it fast process? Is it really suitable for scale-up production in the gigafactories?
The question is on the polymerization of ionic liquids, the scalability, because not all people could hear. So yes, understood.
Yeah, thank you for your question. So actually, the process is based on the polymer is already formed when we apply the polymer onto the substrate, and we mostly have the evaporation of the solvent. So the chemistry itself could be upscale. However, we are still facing many challenges which are mostly related to the achievement of the KPIs. So in principle, the polymer itself doesn't seem to be the main issue for the upscaling. The problem is achieving a working cell with certain parameters in terms of energy density and in terms of capacity. At the moment, the main issue in terms of roll-to-roll upscaling into a roll-to-roll process is mostly related to the cathode, which is prepared according to a solvent inversion technique, which uses more than one solvent, and this process has to be proven in a roll-to-roll process. So we haven't done that yet. Thank you.
Please, other questions? Okay. At the end of the room, and then we go in front. Thank you.
All right. My name is Didier Deveau. I'm a CNRS scientist. Thank you all for those three very interesting presentations. I have also a question for the SOLiDIFY project related to the trench technique to make porosity. Does this technique permit to get some kind of gradient of porosity within the thickness of your electrode? And have you checked how it relates to the C rate, max C rate you can reach with that?
Thank you for your questions. Apologies, I don't have data on the morphology and microstructure on the electrode. However, in principle, the microstructure can be tuned. One issue we are currently facing is mostly related to the low porosity of the electrode, which then leads to a low tap density compared to conventional electrodes, and this may affect the final value we get in terms of energy density due to an increase in thickness of the cell. So at the moment we are still working on finely tuning the process, mostly to decrease the density, possibly applying a calendaring, a mild calendaring, which is something we wanted to avoid to improve the contact area between the cathode particles and the electrolyte solution. Thank you.
There was a question here. Please, Lucy, thank you.
Thank you. Burak Dermenci from VUB, Free University of Brussels. My question is actually to Maria for the SAFELiMOVE project. I was wondering the thickness of the lithium foil you used. Would it be possible for you to share? The thickness of lithium foil you used.
So in the first generation, we were using 15 micrometers, and later we decreased to 40. But we need to consider that it's 50 micrometers layer was used for 2 cell units. So at the end, we have 20 micrometers per unit cell. Thank you.
Okay, there's a question in second line, please.
Yeah, just because I'm sitting so close. My name is Frank Seifried from Volkswagen Research, and I have a question to the lady from the CEA, the first presentation. What is the current thickness of the electrolyte, and what is your target to be achieved in, let's say, 3 years?
At the moment, we have tested some 20 micrometer of electrolyte, but it's difficult to control this because there are some roof surface, in fact. But because there are two electrolytes, there are effectively the membrane that is put on the top of the electrode, but the electrode is impregnated also with electrolyte, polymer electrolyte. It's for this reason that we don't know exactly up to what thickness we can go to avoid the short circuit.
And the internal.
But we have tested the result that I shown was with 20 and 40 micrometer, but we can decrease again.
And this is achieved right now?
Mm?
This is achieved
Yeah.
right now?
Yeah.
And what is the internal resistance then?
I don't know.
Okay.
Yeah.
And last, you mentioned, so far I understood, an ideal temperature level between 50 and 60 degrees C.
Yeah.
So what is the application you have in mind?
Effectively, up to know that we need to decrease again. So this need to be optimized if we consider some new ionic liquids, and if we can again effectively decrease the performance. For the decrease of performance, we need to work with LSZO, because effectively, if you look at the result that we have got with Alcel on the NMC, it should be possible to work at 20 degrees. But as soon as we are with full cell, it's not possible. So it's for this reason that we need to consider also some development at the anode.
Thank you. Are there any additional questions? Bozar, and to make so that Lucy still continue running.
Thank you so much. Bozar Khanbay from BEPA. My question is from the SOLiDIFY project. I'm just wondering, are you aware of any other companies or techniques close to yours? I mean, it looks very promising, but in general, about that scalability, are there any other alternative that has been found by other, I don't know, companies working on this topic? And yeah, if you have time, could you elaborate on the scalability issue a little bit more? Because it seems that at what stage that problem was more pronounced. Thank you.
Okay, we have been also working on a similar chemistry, which it's not based on a polymerized ionic liquid, but it involves the same processing, so where we apply a liquid precursor and then we get the solidification in situ onto the electrode. And this technology is now used by Enamic spin-off. So we are also trying, together with the spin-off, to solve the issues in terms of processing. However, even in this case, the main issue is the mostly related to the times we may foresee for the various steps within the project, the process. So those don't match with the actual times we can foresee for a conventional roll-to-roll process, and they need to be optimized. There is a requirement of specific equipment to ensure the proper aging and processing of the precursor solution. So they are still unsolved issues and still open challenges. Thank you.
Here?
If there is another one.
Okay, there's another one from you behind you. So we go, and then you come here. Sorry.
Hello, here's Ian Five from Bosch. This is a question or a comment or a question to SAFELiMOVE. I was really happy to read on one of your slides, and you mentioned this in terms of learnings, close communication and support between material developers and cell makers. And I have to admit that we wrote a proposal for a project called 5EB nearly 10 years ago, and we wrote exactly the same thing. And I think things are getting better. We see the potential, a huge potential here. The question is, how do we do that? How do we get people to communicate? And there's a problem. The problem is basically the confidentiality. The problem is the say IP when they start talking to each other. So how do we do that in a practical way? Can we use projects to support things like this, learning how to do that better?
So thank you for the comment and also for the question. That's true that this is the learning that I gained during this project. Also, I think the partners of SAFELiMOVE will be agree on that point, and it's not an easy task to be solved. For example, from my personal experience, I work I'm more focused on new chemistries development, so more on the breakthrough ideas at the scale. And SAFELiMOVE, I think, has support us on further understanding how are the challenges more related to the engineering on the final application. And for that reason, I think that there is no one easy way to solve this, but through this type of projects, I think it's a really good way to put all together in common and try to really understand the needs and the challenges that each individual has to face. For example, during SAFELiMOVE, in the first material generation, we were, so thanks that we have these different phases, because in the first development, the first level of material, we were developing the materials independently. And then once we put everything together, we realized how important was to have this communication, because the people involved in producing in larger scale realized that they do not have the capabilities to do in the same way as we are doing at a large scale. So this is really a big issue. And then from that point on, we started to develop a chemistry that was compatible with the capabilities of the partners as well in charge of this manufacturing. So answering your question, I will say that these type of projects are a good way to push this communication and this collaboration.
Thank you. Now here, thank you.
I should have asked the question when Lucy was here. Sorry for this. This is Samaras from Aristotle University. I have a much higher level question, maybe oversimplified things, but it's from my understanding. I'm a mechanical engineer by training, having done a lot of things, hopefully in the area of internal combustion engines and automobiles. But the question goes to SAFELiMOVE, but it applies to anyone. I was making a comparison at your final slide, or one of the final slides, where you were showing where the project arrived in terms of energy density per kilogram, per liter, per volume, which is both very important, as well as number of cycles, which means durability. And I was honestly comparing this to something that we all know is on the web, and it's a Chinese company that sells solid-state battery. At least they are, and the characteristics, they seem better. So they have arrived at these levels, and I would consider them as TRL9. So my question is, what is that we are doing better? Or are we ready? Why is this TRL6 and not already in the market? Or you can ask the question anyway. It's a very simplifying question, but I would like to have your comment or the comments from everyone. Are we running behind something, or we're trying to do something better?
So really tricky question. So, yeah, that's true. So I think that here in the table we can see that there is no magic solution for solid state. All projects were granted 4 years ago. And the chemistries, it may seem, if you really are not familiar with the chemistry, it may seem that they are similar, but they are really different at all the points. Maybe with ASTRABAT it's easier to find the difference because we do not have even the same anode. So for that reason, I think that somehow this call was pushing to try to go from fundamental development of new chemistries up to high TRLs to have the prototype. And that's true that this has allowed us to evolve maybe faster compared if we do not have this type of projects. But it's not easy, and there is still a lot to do. I will say that we have reached TRL6 by means of the type of the prototype. But from my point of view, before going further or going into the market, as you were asking why we are not in the market, I think that there are still many things that should be proven. So many other tests, and of course manufacturing, I think, has been a common challenge for 3 of us, but also related to the safety and performance. There are still things that should be overcome or improved to be there. So that's true that I think there is no clear answer for this. If you want to add something.
Yeah, perhaps it is indeed difficult to identify what we are doing better. In terms of scientific understanding and knowledge, we might have indeed some relevant insight on the various technologies. However, when we indeed evaluate where we are in terms of TRL, indeed we do face some challenges. And yeah, I agree that not just advanced technologies, but when we compare our technologies, even with the conventional configuration, let's say a cell-to-pack system using a simple graphite anode and LFP, and we evaluate the performance in terms of KPIs, energy density, thermal properties, we do see that we are even not matching those targets. So indeed, we need to spend some more efforts in advances in our technologies, identify the actual metrics before or already when we are developing. We are performing the material development. Already at that stage, we have to start estimating what the actual metrics will be in the cell, what the actual, we have to estimate the final KPIs we will get when we will upscale a certain technology to enable us to make a screening already at the material development level without the need of trying certain technologies or developing certain technology, upscaling the technology, and then see that indeed there are challenges, there are problems which perhaps cannot be solved. So this approach in general might be of help, I think. I don't know if that answered your question.
Are there additional questions? If not, I take a comment, and then I have a question for you, if I may, if there's a part, if there's some. On the last topic, I guess that if we are later than Chinese or Asiatic countries. For sure, we started later. But the opposite happened when we started with combustion system. We started before, but this doesn't mean that in China they didn't started producing combustion cars, and they did. So now we started late, and so we are really pushing in research to reach that level first, and then let's hope also be better. Let's see. My question is also for you, related to your projects. I saw that you all this chose as a cathode, high voltage cathode. I guess this was to match the request of energy density of the project. Would it be easier in somehow if you could use a lower voltage cathodes, for example? Could this be closer to market in this case, or what do you think? What's your comment? Someone should start.
Okay. So yes, so you are totally right. So we needed to use NMC mainly because where you were seeing the target of these goals by means of the energy density, the only way to go there, to reach there, was with nickel-rich active materials. If you ask for my personal opinion, I'm really keen, and actually the research activities I lead at CIC Energy Gone are also really focused on LFP type of cathode. I think that there are many advantages. Everything is moving forward to nickel-rich active materials, but we need to consider somehow other nice aspects of the LFP that is more stable, so for the cyclability will be much better, compatibility into the cathode side, of course, and also for the processing, we need to consider that we would like to look for green processing, so water-based, and I think LFP can be there already. We can process LFP in water, there is no issue. Also, we don't need strict conditions for the processing, so we do not need a dry room. While in the case of the NMC, and the higher the nickel content, the most difficult is this challenge, so we may struggle with this part. So if you ask for why NMC selection is this, if you ask my personal opinion, I will not discard other type of other materials, active materials.
Yeah, I also personally see LFP as one of the best candidates which we may use in those systems. We are seeing that LFP perhaps is having a new golden age, so there is a renewed interest in this type of material, especially because of its high thermal stability and its cell performance, which then make it particularly suited for these new cell-to-pack systems, where we can get indeed very high energy density, although the energy density at material level is not the same as what we can expect from NMC 811 or 622. Using LFP would solve many issues in terms of recycling, in terms of cost, in terms of cell performance, in terms of parasitic processing in the cell. So indeed, yeah, it is perhaps an area which we could explore more, even in terms of upscaling.
So effectively, in ASTRABAT, we have used NMC 811. The stability, when we have done some tests in liquid electrolyte, effectively there are some small decrease also after cycling. So in comparison with LFP, the LFP is stable, yes. But the energy is not the same. Yeah. So after, it's also related to the cell architecture that you will use, if you can use correctly the electrode materials. LFP has some interest for the safety aspect, for the recycling. So I think effectively it's something that is more and more considered again for the automotive industries. Yeah.
Thank you. There was a question here. Yes, so an additional question. Thank you.
Thanks a lot. I'm pretty convinced that some elements might lead to a larger LFP deployment in the future, also due to the opportunity of using batteries, mobile batteries as well, for grid services, potentially B2G, etc. But I was wondering, on the recyclability, it's for sure safer to recycle, but the point is that isn't the material, my doubt is the cathode material then so cheap that it actually doesn't have any business case for recycling?
Yeah, I don't work in the field, so I'm not an expert in the field, but indeed that's a very good point. I know it's also one of the concerns we may have also on some alternative chemistries which have been proposed over the past 20 years. So indeed that is one of the issue which where we need to identify alternative strategies and a high efficiency for recycling, which may lead, may improve the advantage of recycling the battery. Yeah.
The comment? Other questions? Maybe different way of recycling. Now we are strongly pushing on direct recycling and other methods for lower cost materials like LFP as an example. Then registration pushes us properly to recycle everything, so no doubt on this. Is there any additional questions? So just a question, a perspective question. So what you are expecting for future? What we really need to upscale and go to further improvement of this kind of chemistries? Let me say, more efficient materials, better companies producing materials, I don't know. Just please, if you can just give us your view on this. Maybe we go on the other side, starting from Sophie, so changing the order than before.
No, but I need to. For the future, I think it's clearly need to have more materials available. At the moment, there's some difficulties to find some producer of raw materials. When we said raw materials, the initial materials, there are some two or three big company and not sufficient variety of production. And due to that, this block more or less the possibility to develop some new material, new technology. So I think it is something that is important to consider also. And after, effectively, in Europe, the idea is when we said that we would like to develop lithium-ion battery, gigafactory, we need to develop also some new patent and some knowledge for new architecture that could be really efficient in the future. It's perhaps this that could be the next step. And effectively, at the moment, there are Chinese company, Asian company that are the first, but we need to find some other solution related also to recycling. If you would like to recycling, you need to find some design of the battery that could be easy dismantled for the recycling and have an efficient recycling and business model associated to this. So it's for this reason that there's still a lot of work, effectively, to do.
Please.
Yep. So I agree from my point of view with the points highlighted by Sophie, and just to add something that maybe is not fully related to technological restrictions for the manufacturing, I would say before, in this case, I will say knowledge, because since this is still not mature enough, these chemistries or this technology, I think that we still are missing to really understand what are the main limitations and how to tackle them. For example, with the lithium metal, the reactivity, there are many patents, papers, reports where you can see how important it is to solve the reactivity, but there are also still, I think that we are missing if we consider how this will be in a long-term basis, how this will affect, how we can solve into the battery, and also from the very beginning, when we consider the manufacturing, even how is the effect of exposure in the lithium metal where you are assembling the cells in a gigafactory, if we consider, at certain dry room conditions, because since it's too reactive, how this will affect on a long-term basis, for example. So I think that there are still things that we need to really understand in order to be able to solve and to have a technology mature and enabling the performance that we want.
So I also see some issues which are for sure related to the availability of high-quality materials, raw materials in Europe. However, within SOLiDIFY, we also identified some issues which might be intrinsic to the actual chemistry. So unfortunately, we do have a trade-off between mechanical properties. We observe this trade-off between mechanical properties and rate capability of the cell. So it's difficult to achieve certain mechanical characteristics of these systems and at the same time ensure a rate capability which matches the targets set within the call of the European call, and then identified in the various projects. One issue indeed is the reactivity with lithium and the high reactivity of lithium, formation of lithium dendrites. So we are seeing that the anode protection is one of the key strategies which may ensure reversible operation of the cell. And another aspect which has to be considered, which is, I think, intrinsic of this particular technology, is the large volume variation which we experience. So, for example, I mentioned earlier something around 10 or 12 million per hour per centimeter square. That would correspond roughly, I think, to something around 50 or 60 microns of lithium, which are plated on the anode. So if we start with for example, the anode we are currently using as an overall thickness of 30 microns, where around 10 microns are the current collector. So we start with 20 microns and we plate on top of it other 60 microns. And this has a huge effect when we upscale the, and when we move from the cell to a multi-layer cell, then we move from the cell to the module, then to the pack. And those questions are still open, and alongside the questions on the lifetime due to the dendrite formation.
So, messages for the next strategic research innovation agenda. Okay, if there's no additional question, I guess that we have a longer time for coffee or to change the room. So I thank you all, and maybe...
Certainly looks like it. So the next session is then starting at 4:15. I think Lucie is... oh no, yes, there they are. I would also like to invite you to have a look at the stands if you haven't already done so. And then finally, I would like to ask you to give a round of applause for the 3 speakers and for my co-moderator. Thanks very much for your attention.